Okay, so this is problem 15.49 from Mastering Physics. So chapter 15, number 49. The problem says it's possible to use the ideal gas law to show that the density of the Earth's atmosphere decreases exponentially with height. That is, rho, so the density at some height z is equal to rho naught, e to the minus z over z naught, where z is the height above sea level. Rho naught is the density at sea level, and z naught is called the scale height of the atmosphere. Determine the value of z naught. What is the density of the air in Denver at an elevation of 1,600 meters? And what percent of sea level density is this? So that the density of air in Denver we would expect to be less because it's above sea level. And we know that the density of the air decreases with increasing height. So, step 1, draw a picture. This is my picture. So I'm going to take a column of air over the surface of the Earth. And that column of air, I'm going to look at a little element within that. Call it dz at a height of z above sea level. So that's all I need in my picture. What other things do I know? I know that the atmospheric pressure is equal to 1.013 times 10 to the 5th pascals. That means that at sea level, the weight of that column, now I have to give it some reasonable cross-sectional area, and why not just give it a cross-sectional area of 1 square meter? So basically we're looking at a column of air, a cylinder, with a cross-sectional area of 1 square meter. So if I take that pressure at sea level, remember Pascal is a Newton per square meter, times the cross-sectional area, I get the weight of that column. So that's the weight of the column, 1.013 times 10 to the 5th newtons. So that's the weight of that column at sea level. So what about this slice? What's the weight of that little slice that I've drawn in my picture? Well, let's start with the volume. We're going to need to know the volume. So what's the volume? Call it dV. It's equal to the cross-sectional area times dz. So then dW, so if I look at the weight of that little element dz, it's dm, take the mass, times g. But we can fill in something more specific for dm. We can say rho times dv is dm times g. So that's the weight. But we already solved for dv, so let's plug in for dv. Take rho times g times a dz. And that's also equal to rho times g times 1 square meter, we decided, times dz. So now we can plug in because we know the density. So this little weight dW, plug in for the density, rho naught, e to the minus z over z naught, times g times 1 square meter times dz. So remember up here we decided the weight of that entire column was 1.013 times 10 to the 5th newtons. We can use that now. The weight of the column is equal to the integral of all the little elements. So the integral of dW, where W is the weight. So now take the integral from 0 to infinity fill in rho naught, e to the minus z over z naught times g times 1 square meter dz. So then if we do the integral, you're going to get rho naught times g times 1 square meter e to the minus z over z naught, and then there's a z naught that comes from doing the integral. We have to plug in the limits of integration from 0 to infinity. So z goes from 0 to infinity. So you get rho naught times g times 1 meter squared z naught. Why do we carry around this 1 square meter? Well, for the sake of unit analysis. So we'll end up with weird units if we don't remember that we used an area of 1 square meter. And from our limits from 0 to infinity, well, 0 means that's where z starts. Where 0 is sea level. And then infinity, well, the atmosphere is going to extend out into space, and yes, at some point the atmosphere goes away. And so basically from 0 to infinity, well, a very large distance away, the atmosphere goes away entirely. So we just call that infinity. So now solve for z naught, because remember, this expression is equal to the weight of that column that we defined. But the weight of the column is equal to 1.013 times 10 to the 5th newtons. So now set our whole expression . 1.013 times 10 to the 5th newtons equals rho naught g times 1 square meter z naught. Now solve for z naught. Z naught equals 1.013 times 10 to the 5th newtons divided by 1.28 kilograms per cubic meter. That's what rho naught is. Density at sea level times 9.8 meters per second squared times 1 square meter. So our units work out. And we're going to end up with 8.08 times 10 to the 3 meters. That's our scale distance. So now we want to solve for the density of air in Denver at an elevation of 1,600 meters. Go back to our original function and plug in what we know. So rho is equal to rho naught, 1.28 times 10, or rather 1.28 kilograms per cubic meter. And then we have e to the minus z over z naught. But now we know z naught is 8.08 times 10 to the 3 meters. So now if we plug in 1,600 meters for z, we're going to get that the density of the air in Denver at 1,600 meters above sea level is 1.05 kilograms per cubic meter. And then they ask, what percent of sea level density is this? Well, because the density decreases with height, we would expect the density in Denver to be less, and it does come out to be less. 1.05 is less than 1.28. So let's just take that fraction, 1.05, divided by 1.28, and we get 0.82. So that means that the density of the air in Denver is 82% sea level density.